All right, section 8.2, we had two more examples at the end, and in fact, one of them is thrown in here because I want you to not assume that simply because you're in section 8.2 that it's always integration by parts. So we're going to take a look at part D. I believe that's when we're on. Is that correct? All right. All right, so taking a look at this one, we've got an x, and we've got that x minus 5 underneath the square root. And it looks like it's multiplied together. I mean, well, it doesn't just look like it. It is, right? I mean, each of those two pieces are multiplied. It very much has the same feel as the ones we've been working with, where we've been looking for, these integration by parts, this u and du and v and dv. But this one doesn't really need u substitution, although it still has, it doesn't need integration by parts, although it still has that same feel to it that the others have. So I wanted to show you when you have a situation like this that we don't actually need. Our u substitution, plain old u substitution, will work just fine. So if you're taking a look at this one, what do you think you might let your u be? X minus 5. Now, at first glance, that doesn't look like you've changed a lot, especially because most of the time when you do du, you don't end up with 1, and you do here, don't you? So it doesn't really look like that's very helpful, but it actually is quite helpful. The problem with this one that makes things difficult is that there's subtraction underneath the radical. Right? You don't have any properties that allow you to separate out radicals when there's subtraction or addition underneath them. If it were multiplication, that'd be great. If it were division, that'd be great. We could separate out that radical somehow. But with the subtraction, we can't. So this is actually going to be really helpful. Here's the one piece that we need, though. Well, I'll move it down here. We're going to take that u equals x minus 5, and we're going to also solve it for x. So what does x equal if u is equal to x minus 5? It's u plus 5, right? Okay, good. So we can take this integral, and we can rewrite it. That x that's on the outside can be written as u plus 5. And then the x minus 5 that's underneath my radical can be written as just u, right? And dx and du are equivalent in this case. So is everybody good with that rewriting? So you might look at that and say, well, all we did was put the negative, or the subtraction, if you will, or the addition in this case. It's on the outside now instead of the inside. What difference does that make? All the difference in the world. Addition and subtraction outside of a radical are easy to deal with. It's the addition and subtraction underneath it that make it messy or complicated. So on this case right now, what we can do is we can think about that square root of u as u to the 1/2, right? So I've got u plus 5. And I've got u to the 1/2. Now what? Distribute, you bet. So now I've got u times u to the 1/2. So here is your chance to redeem yourself, those of you who were struggling with some exponential rules in the last test. What is 1 3/2? Thank you. We add exponents. This is u to the 3/2 plus 5u to the 1/2, right? And we can integrate those, right? Absolutely we can. So what is the integral of u to the 3/2? Okay, 2/5 u to the 5/2, right? So we increase that exponent, which is 3/2, by 1, making it 5/2. And then we would divide by the new power of 5/2 or multiply by the reciprocal 2/5. So that's half of it. Now we have the integral, well, here's my 5. We have the integral of u to the 1/2. What will that one become? Okay, so there will be a 2, because 2?
I multiplied through.
Oh, you multiplied something through. Okay, so somebody told me it was u to the 3/2. So this will be times 2/3. I think that's right, because you were telling me 10, or Erica. Yeah, okay. I need a plus c. All right, so 2/5 u to the 5/2 plus what? 10/3. Good. U to the 3/2 plus c. What's left to do? plug that back in. So a couple of things here. I'm going to move this over just because it's going to be a little bit more space. So I have a 2/5. This is U. I said 2/5. Let's write it right. 2/5. U is x minus 5 to the 5/2. And then I have plus my 10/3. And this is x minus 5 to the 3/2 plus c. How else might you see that written? It's fine if you leave it here, but how else might you see that written if you were sort of checking the back of the book or if you were checking your answer with someone else and they had gone further? You might see it with square roots, right, with radicals. So you might see something like this. So I have space on my slide, I do. Let me just show you some variations of this, just because I want us to all be aware of how you can change it, not because I expect you to. Please don't think you need to do anything you don't. This answer is just fine. So we might see this written something like this. Right? I did it again. Thank you. Yep. Any other ideas? There's another thing you could see happen if somebody kind of wanted to keep going for some odd reason. They might try and find a common denominator. That wasn't where I was headed with that, but that is a possibility as well, Kirsten, yes. The other thing that you might see is, notice since you've got square roots and you've got powers that are greater than 2 underneath those square roots, you might see something simplified there. So you might actually see this written, and simplified isn't even exactly the right word here, but you might see this written as x minus 5 squared and then square root of x minus 5, where 4 of those come out as 2, right? And 1 is still left underneath the radical. And again, you might see this written, I'm really having a difficult time with the exponents, or the denominator of that too there, aren't I? 10/3, you might see this written here then as x minus 5, square root of the x minus 5. If somebody wanted to get real creative, they might decide that they want to factor out the square root of x minus 5. They might do something with the denominators to get a common denominator, or they might even factor out the x minus 5 that's outside of the radical. All of those are possibilities if you had to do something with this further on for some reason. But as you're taking a look at this, does it really look any simpler than the one I told you could stop with? It looks more complicated, yeah. I mean, it's getting messier as I go, right? So there's not a need to continue with this process. If you do, it's okay. I mean, if you think that you're going to be able to simplify something and finally realize that it's just getting messier. But the first one that we had is just fine. And we're going to leave it that way for our solution. Those are just other variations underneath. Any questions on that one? All right, so again, taking a look at the original problem, the reason that we would want to try to do something here is because we notice that we actually have underneath the radical a subtraction. If you had addition or subtraction underneath the radical, a U substitution might be enough to take care of the problem. All right, we have one more example. The last example, how is it different than the ones before? It's definite. It's got limits of integration on there, right? So we're going to still be working with, when we're working within the context of doing something where it looks like we have a product. The other difference on this one potentially as you look at it is I don't see a product. Do you? It really doesn't look like one. It doesn't look like the other ones that we've had. If you take a look back at this packet that you were working on last time, the other ones that we have all actually look like you've got things multiplied. The first one was x cubed times natural log of x, 2 pieces multiplied. The second one was x cubed times e to the x, 2 pieces multiplied. The third one was e to the 2x times sine x, 2 pieces multiplied. This doesn't look like that, does it? But U substitution won't be helpful. And integration by parts actually does work. So when we start with integration by parts, we have U and du, and we have v and dv, right? Where do we actually have to plug values into from the original given information? What two pieces get parts plugged in? U and dv. Very good. Somebody tell me, without looking back, just look up here, what are some of the guidelines that help us make those decisions?
Natural log has to be U.
If you've got a natural log, it has to be inside of U. We talked about that one last time. What else? Yeah, so you're looking for something that either maybe gets simpler when you take its derivative, or maybe that gets simpler when you take its antiderivative, something like that. So if you've got something that actually gets easier to work with, it's often helpful to put that into U, because when you take its derivative, it will get easier. Yep, that's another feature. Anything else? Sometimes the dv, you have to make the decision simply because it's all that's left. I mean, it's the piece that's left over. And that's actually what's going to happen here. So, Michaela, you mentioned letting the u actually be the natural. All right, so this u down here is going to be the natural log of the 4 plus x squared. Remember, natural log doesn't mean anything apart from what's inside of it. It's kind of like if you just wrote square root. Well, square root of what? Okay, natural log of what? So the natural log and the piece inside are connected, so all of that goes there. Now that looks a little weird because it doesn't look like I have anything left to let dv be, doesn't it? But I do. What do I have left? I have a dx. It doesn't look like a lot, but it's enough. Let's do the part that's sort of a little more intuitive maybe first. What's the derivative of the natural log of 4 plus x squared? How do you do that? 1 over. Good. 4 plus x squared. Not yet. Times 2x. And then my dx. So I'll take a step here just to rewrite this. So this would be 2x over 4 plus x squared, right? Okay, let's go over to the other one. What is the integral of dx?
X.
It's x. Yes, it is. Oops. Getting carried away with my dx. It's x. All right, any questions on that so far? All right, so now we're going to have to remember back to like 5 days ago. What do we do next? We've put everything in there. We've identified, we've integrated, we've taken derivatives. Now what? Okay, so we multiply across the top u times v. So this is x times the natural log. In fact, I'm going to run out of space. I'm going to put it down here at the bottom. So this is x times the natural log of 4 plus x squared. Now what?
Minus the integral of u dv.
Right. Well, the other one.
Du and
Yeah, v and du. So these two. Right? So I'm going to take those two pieces and I'm going to multiply them after this integral. So what's that going to give me if I sort of combine those together with multiplication? Good. 2x squared over 4 plus x squared dx. Now what? We're going to have to do an integral of 2x squared over 4 plus x squared. How do we deal with that? We won't need another u or du or v dv. Yes, you can. Say that really loud for me, David. Long division. Why in the world would this be long division?
Because it's got the same exact exponent.
They have the same exponent on top and bottom, don't they? That's one of those things. Anytime we have an exponent on top that is at least as big as what's on bottom or bigger, that's a long division issue. And that's what we've got here. So we are going to do long division. I'm going to do my long division on this screen, then we'll flip to the other one after I have taken care of that. So The part on the outside is the divisor, 4 plus x squared. If you prefer, in fact, I kind of prefer, so I'm going to switch it. I'm going to write it as x squared plus 4. And then underneath is the 2x squared. If you want, you can put plus 0x plus 0. I'll do it just for the sake of having done so, because a lot of times it's helpful to see. In this one, I don't think it's all that crucial, but it's okay. All right, so long division, we haven't done that in a while together. You guys did a couple of them, I believe, on your homework. But we haven't done that in a while together. When we look for long division, we consider the first piece of each of these. I've got an x squared and I've got a 2x squared. And I basically ask myself this question: what do I need to multiply x squared by to get 2x squared? And the answer would be 2. So we're going to put a 2 here, and then we're going to do the multiplication. 2 times the x squared is the 2x squared. And then 2 times the 4 is actually 8. So I'm going to put it up over here. Underneath is the last 0. And then what do you do when you division? You do division. You subtract, and subtraction is the equivalent of changing all the signs, right? So we've got these both subtracted now. So this piece goes to 0, which was the whole point. I mean, that's how we made the decision to put the 2 above anyway. And the last piece becomes the negative 8. So what happens is that this piece down here that I was working with to do the division for became 2 minus 8 over x squared plus 4. Okay, these are equivalent expressions. Difference being that the new one that's in blue I can work with. The previous one was not in a form I could work with. Okay, so I'm going to go to my next screen when you guys are ready, so just let me know when I can flip to the next screen. Good? Okay, so right now we have x natural log of 4 plus x squared minus the integral of 2 minus 8 over x squared plus 4 dx. Did all the pieces in there correct? Yeah. Okay, just for clean looking work, I'm going to change a few of these things around. I'm going to write this the same order. I'm going to distribute that negative through, so this is actually minus the integral of 2 dx plus the integral of 8. In fact, you know what, I'll put that 8 on the outside even. 8 times the integral of 1 over x squared plus 4 dx. Is that okay? All that kind of combined. You don't have to do that step. I just like seeing it myself. So it's up to you. All right, so the first piece, of course, is already done. I have x natural log of x squared plus 4. What's the integral of 2? 2x, good. Now what is the, well, I'm going to put my 8 down. What's the integral of 1 over x squared plus 4? Is it natural log? It's arctangent on this one. Okay, so here's a point to pause, because this is a real common sort of thing we think denominator means I'm going to get a natural log. Why is this one not going to become a natural log? The denominator has a piece in it that's squared. That's one of those sort of red flags. The only time the natural log comes into play is if the denominator is a linear factor. That is, it has to have just plain old x. It can have addition and subtraction if you want, but it can't have x to an exponent. So natural logs won't work here. But this does have the form of arctangent. So arctangent of what? Well, when we have arctangent, we have to identify what the a value is. What is the a value in this problem? It is 2. Okay, so using arctangent, there's a factor in front. I've got an arctangent, and then I've got something inside of here, right? All right, so what's in front?
1 over 2.
Yep, it's 1 over a, and a is 2 here, so this is 1/2. What goes inside of the arctangent?
U over A.
U. And my u in this problem is what? Just x, yeah. So the u is actually just x. So this is x over a, which is 2. If this were a indefinite integral, I'd put a plus c and I'd be done. But it wasn't. It had some numbers in it, didn't it? Yes, it did. 1 and 0, I think. So we need to evaluate this at 1. It's okay. So we need to evaluate all of this at 1. We need to evaluate all of this at 0. And just because it's 0 doesn't mean things go away. They do with polynomials, but they don't always with trig functions. And we've got an arc trig function here, so we need to be careful about that fact. All right, so let's evaluate this at the value 1 first. So I have 1 natural log of 1 squared plus 4, which is 5, minus 2 times 1, which is 2. 8 halves is actually 4, times the arctangent of 1/2. Okay, and that's all of the evaluation at 1, right? Now let's evaluate what happens at 0. So when I put the 0 in, what happens to the x natural log of x squared plus 4 piece? That is 0 because the x at the beginning right here means I'm actually going to multiply a 0 through to it. The next piece, 2 times 0, also becomes 0, right? And then I've got plus 4, and I have arctangent of 0, which may or may not be 0, because we're dealing again with trig functions. This isn't a 0 times something here. So we need to actually evaluate that to make that decision about whether that's 0 or not. All right, so let's kind of simplify what we have. I've got the natural log of 5 minus the 2 plus, all right, so arctangent, arcsine, arccosine, when we are dealing with evaluation, we have to think about our unit circle, right? Okay. So if I were dealing with arcsine or arccosine and I were dealing with the 1/2 feature, that would actually have a function value that I know. It would either be a 30-degree or a 60-degree angle. Okay? Because the arcsine and the arctangent, or the arcsine and the arccosine of 1/2 is a value on my unit circle. But the arctangent doesn't have that feature. Arctangent means you're dividing the coordinates by each other. So what kind of values could you be looking for an arctangent to actually simplify? Can you think unit circle with me for a minute? There are 3 possible angles. Well, actually there's 5. There's these points right here. Your unit circle. So this one right here is 1, 0. What's the second coordinate? Square root of 3 over 2, 1/2. What's this one? What's this one? And the final, square root of 3 over 2, right? So we're looking at those unit circle values, and then up here at the top I have 1, 0. All right, so let's think about tangent values at each one of those unit circle locations. Oh, I wrote it wrong. I'm sorry. Thank you. Yes, it is 0, 1. Okay, so how do you get tangent values when you've got those ordered pairs? Sine over cosine, which is the equivalent of y over x. Y over x. It's actually like slope, y over x. So we have y over x. If I were finding the tangent value here, the tangent value of this angle, y over x, would actually be what? This would be 0. So what is my theta value when I have an arctangent? So if I were to say this, theta equals the arctangent of 0, that's actually something that I'm looking at. It's the last piece right here on this problem, isn't it? What angle measure has that happening? Where's that happening? That's a 0. This is an angle measure of 0. So the arctangent of 0 actually is 0 on this one. So all of this function value right here really is 0. So I don't have anything on that one. Let's move up here just to make sure that we remember how arctangent works a little bit. What happens if you take this piece? What happens if you divide the y value by the x value at this 30-degree angle? So So this is at 30 degrees, which is the equivalent of pi over 6. You get the 1/2 over the square root of 3 over 2, right? Which is the equivalent of, is it square root of 3? Square root of 3 over 3. There you go. That's a square root of 3 over 3 value. That's not what I have. I have the arctangent of 1/2, right? So if I were to flip this around, this would be saying that the pi over 6 value is equal to the arctangent of square root of 3 over 3. Well, I don't have square root of 3 over 3. I have 1/2. So that's not it. What happens on this one? What is the tangent at pi over 4? That's 1. So again, if I were to think about this reverse, this is saying that pi over 4 is the arctangent of 1. I don't have arctangent of 1, but if I did, that'd be a helpful feature to have, right? Over here, I've got a very similar fact to what I had with the tangent of pi over 6. So the tangent of pi over 3, what is that? It's actually square root of 3, right? So if I were dealing with this one and I wanted to know the arctangent of square root of 3, and I think we've encountered that one before, I would actually have pi over 3. What happens at the top here? It is undefined. So this one's not one we're going to have to deal with when we're looking at evaluation because it doesn't, I don't have a limit of integration that says undefined, right? So the gist of this is none of these actually match up to arctangent of 1/2, do they? So I don't have a unit circle value, which means I actually get to leave this one as is. This is for arctangent of 1/2. And this is the exact solution. Now, of course, if you were asked to find this is strange. If you were asked to find an approximation for this, the 3 decimal approximation, which your book does, sometimes you could be asked to do that. You could find that, right? Excellent. Any questions on this? Okay.